a visiting professor at Stanford as well. He has been professor at Carnegie Mellon. He has won an enormous host of awards. Very prestigious Maurice Wilkes Award for early career excellence in computer architecture. He's a fellow of the ACM, fellow of the IEEE, has won all sorts of best paper awards, Test of Time Award, IEEE Edward McCluskey Award, and I could talk about all of them, but then he wouldn't have time to give his talk. And I'd rather listen to Onur than listen to me list Onur's bio. So with that, I'm going to turn the stage over to Onur.
Okay, thank you. Thank you very much, Dan, for the kind introduction, and thanks, Jiran, for inviting me here. This is my first time giving a talk at the Duke campus, actually. Last time it was, I think, at NCSU, although I visited briefly over here. So it's good to be here. I should warn you, I have a lot of slides. It's a topic that I'm quite excited about, and we've been doing a lot of work in this area. I'm not going to cover all of them. I'm going to cover some of them at high bandwidth. We should all be high bandwidth memories, right? That's I got to do what I preach. But feel free to stop me at any time. We don't have to cover all of these slides. And clearly, this is an exciting area where I believe there will be a lot more development going into the future. And we need to do research to enable a new computing paradigm. Okay. Well, if we get computers working. Okay, maybe my computer. Okay, so I think it's clear that today computing is bottlenecked by data. We're seeing this in many applications. Important workloads are all data intensive. You look at machine learning, genomics, video. These all require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process. And we need to perform more sophisticated analysis on the data as applications grow and we become more sophisticated. I'll give you some examples of this, and I'll put some numbers to this also. So clearly, neural networks, everybody's excited about them. These have been growing. This is a beautiful talk by the Cerebras CEO, CTO maybe. Basically, these guys are building these chips that are wafer scale, large like this. There are a lot of challenges over here. And clearly, they're doing this so that they can put large amounts of computation close to large amounts of memory that could be accessed relatively fast. So this is one way of actually trying to keep up with the memory requirements and the compute requirements growing exponentially. I'm not suggesting this is the best way of doing things. I think we will probably go this way before we figure out how to do it more efficiently. But this is how things are going in neural networks today. By the way, before I continue, how many people here are PhD students? Okay, how many people are master's students? How many people are undergraduates? Okay, a few. How many people are faculty? Okay, and anybody else? Okay, there's also others. Okay, so clearly you may have seen this, or you may be working on machine learning also. But it's not just machine learning. There are many applications that are actually bottlenecked by data today. I'm going to put some numbers about these later on. Data is really a performance energy bottleneck in many workloads. And on the mobile end also, we're having a lot of difficulties, especially with energy efficiency constraints. I'm going to talk very little about genomics. It's an area actually about 1/3 of my group does a lot of work on both algorithms and architectures. And this is an area where data is actually growing potentially even more rapidly than in machine learning, in fact. Basically, this is because we have these device technologies where you can generate sequences of RNA and DNA, and going forward, proteins, et cetera. And you can do this very, very efficiently today in terms of cost. So this picture shows the cost of genome sequencing reducing exponentially and compared to Moore's law, which is the cost of a transistor, essentially. So basically, we can generate much more data than we can put transistors on a chip. You can think of it that way. And this is important because sequencing enables a lot of scientific discoveries as well as medical advancements. We've seen this with the COVID pandemic recently. But we're really bottlenecked by how fast and efficiently we can process this data. And I'm not going to talk about that. I'm not going to turn this into a genomics talk. That's a totally different talk. But clearly, there's a lot you can do if you can have faster, scalable, and more efficient genome analysis. But I will give you one example. This is a paper we wrote a while ago. Essentially, we look at the computational bottlenecks of analyzing the data that's generated by this data generator. This is a genome sequencing device, nanopore sequencing device. It's very fast and very efficient. It's portable, as you can see. Unfortunately, it's quite dumb. Basically, it cannot process any of the data that it generates. So you have to move the data somewhere, usually to a data center, because your laptop is not sophisticated enough, depending on the analysis you do. And you cause a lot of churn, basically, by moving the data. And this talk is all about data movement and localizing the data and processing together. Okay, so that was a generator. So this is another generator. It's another genomic sequence analysis device. This is Illumina. It's much more expensive. Basically, this picture exists in most analysis that we do today. Basically, we have very special purpose machines for data generation. This could be some genome sequencing device. This could be a video camera, for example. And then we move the data far away from that device and do the analysis on usually general purpose or somewhat general purpose machines. So this causes two major problems, in my opinion. One is you have large amounts of data movement, both at the macro scale as well as the micro scale within this thing over here. We're going to talk a lot about that. And also you have mismatch in terms of the capabilities of the devices. This is very specialized for the data that it generates. This is not so specialized on how it operates on the data. It doesn't really understand the characteristics. I think we need to fix these two problems going forward. We're doing a lot of work on making machines match the data characteristics. I think we need to do more on that. But I don't think we're doing a lot of work on minimizing data moments. And this talk is going to be on the data moment part. Of course, there's work that's going on, but industry-wide, there needs to be more done. Okay, if you're interested in genomics, we've been writing a lot of articles. This is an area that's not easy to get into. So if you're interested, you can take a look at some of these things that we've written so that people who don't know a lot about genome analysis can get into it. Okay, so I'm giving you some examples. I think the message is data really is overwhelming our machines today. Storage capability, communication capability, and computation capability. It also is greatly impacting robustness, energy, performance, cost. Essentially, all metrics we care about. Now, if you go back to fundamentals, when you design a computing system, you need to have three major things: computation, communication, storage, and memory. And the way we have evolved these systems is by decoupling them. And that decoupling has enabled growth in these different industries, let's say computation, communication, storage, but it's causing a lot of problems right now. And we did not only decouple them, we made computing unit the only place where you can process the data. So everything else in the system, which is really the most of the system, or overwhelming majority of the system, cannot do anything on the data. You have to move the data to this computing unit, which could be a CPU, GPU, FPGA, and the micro scale, it's essentially logic, and so that you can process the data. So the question is, does it really make sense to do this? So this is my picture. Actually, this is from my earliest NSF proposal when I was at CMU. I still can use the same picture. Essentially, you have a modern multi-core system. You can replace the cores with accelerators or heterogeneous things. So the red parts over here are cores. Those are the parts that can do computation. Everything else within the system is there to move data or store data. Caches, interconnects, other caches, other interconnects, memory controls, other interconnects, other caches, other interconnects, and storage. So if you actually do the calculations, more than 90%, 99% actually, in some cases, of the system is dedicated to storing and moving data, if you look at the big picture, not just a single chip. Unfortunately, the system is still bottlenecked by memory and storage, right? So if you actually give this picture to a kid who is 6 years old, for example, and say, oh, I've dedicated all my resources almost for data movement and storage, so I should be doing great on that end, right? But we're not, basically. So I'm going to give some numbers to this also. So maybe the kid would say, maybe you're doing something fundamentally wrong. So if you don't like my picture, this is AMD's, one of the recent chips. You can see that that green box encapsulates L2 and L3 caches. And then there's the memory interconnect, et cetera, that I didn't encapsulate. So most of the chip is basically data movement and storage. And we're adding more of that 3D stacking. These are beautiful technologies, but we're adding more caches and more data movement and storage with relatively little benefit. If you don't like AMD, this is IBM, and I could keep doing this. But I like this one. This is an SoC today, right? Basically, an SoC is a lot of SRAM today. And then there's the darker part, DRAM, and there's the real darkness, which is storage, which we don't normally think about. And then there's a sensor that I'm going to put both. OK, let me put some numbers. We did a lot of studies on understanding the impact of data and memory on performance, energy, et cetera. I'll start with energy, because I think that's going to be critical going into the future. We analyzed these 4 workloads together with Google in my previous sabbatical a while ago. And we found out that more than 60% of the entire system energy on mobile devices is really spent on data movement. And this is the average case. I wouldn't say these are the most intensive workloads. Later, we repeated this sort of study on the Google Edge TPU. And we found out that, especially on large machine learning models, more than 90%, and in some cases, more than 99% of the entire system energy is spent on memory, both accessing and moving the data across memory. So I think going forward, I'm going to posit this axiom. Basically, we need to have intelligent architectures because they're going to make decisions for us in all domains. I believe they need to handle data well. So the question is, how do we handle data well? This is actually a bigger research agenda that we're following. I'm not going to talk about the second and third parts. We don't have a lot of time. Essentially, we need to ensure data doesn't overwhelm the components. So we really need to rethink the entire system we design. These two other things are also important. I will very briefly mention, we need to have more intelligent architectures that can basically evolve and make better decisions over time. So use machine learning inside the hardware itself so that you can make better decisions. This is fascinating. We have some work in the area. I'm not going to talk about that. And finally, we also need to have architectures that understand the properties of the data, because data has lots of properties: privacy, security, compressibility, fault tolerance, approximability, etc. These properties are not even discovered at the higher levels, let alone communicated to the lower levels. But if you actually understand these properties and communicate it to the hardware, for example, hardware can make decisions that are much more intelligent about using the characteristics of the data. We call this data-aware architectures, but I'm not going to talk about that. But these are actually related, I think. So let's jump into the data-centric part. And I think all of these require rethinking the entire stack. But hopefully, I'm going to show you some simple methods, especially in the data-centric domain, so that we can get there step by step. OK. Any questions so far? OK, I'm going to use some time for motivation, and then we're going to delve into some detail. So when you think about architecture as data-centric, even then you open up some new areas, right? Basically, I think I'm going to talk a lot about processing data where it resides, not moving the data, doing the operations on where the data is generated.
How are you, Kamala?
Is there a question? Oh, OK. Somebody on Zoom, maybe.
I was going to ask a question.
I think we need to design much more low latency, low energy architectures to enable data access. This is something that we need to work a lot more on. I'm not talking about memory hierarchies, but actually memory devices that are much more lower latency and lower energy. This is going to be much more important going into the future. Low cost is important, of course. Intelligent data management. I'm going to talk a little bit about that. Again, I'm going through this relatively broadly because we don't have a lot of time, but I'm going to focus on the first part. So I call this processing data where it makes sense. Basically, we have a lot of places where we can process the data. Why are we restricting ourselves to a small portion of this SRAM chip, let's say? I call it SRAM chip, of course, as a joke, right? But most of it is really SRAM in the end. So why don't we process data everywhere and then have these different components interact so that we can solve much bigger problems much more efficiently? This is not a new idea. These are some of the oldest papers that I could find on the topic. This is the general idea of processing in memory. These folks, Kautz and then Harold Stone, who has a beautiful computer architecture textbook, actually, that he wrote in the 1990s. These folks looked at the idea and they proposed it. And over like 5 decades or so, this idea has been looked over and over in different ways. So you may be asking the question, why should we look at it today? Right? Because I think today is different. Well, today is different in 2 ways. In my opinion, we have nowhere to escape. So we have the technology layer and we have the application and software at the higher end. Nope. I don't know. Should I allow recording?
We're recording it to the cloud.
Yeah.
Anyway.
OK. OK, I'll just deny that. OK. OK. OK, sure. Basically, we're having a lot of difficulties with the data storage devices that we're building, especially DRAM, but also in storage, and that's going to become worse. For example, memory technology scaling is not going well. I'm going to very briefly talk about RowHammer. We're having basically a lot of reliability issues, which manifest themselves as security and safety issues, robustness issues as well. And many of these scaling issues demand intelligence inside the memory, meaning you need to put some sort of computation inside the memory to fix some of these problems. And we actually know how to do this with SSDs, for example, storage. If you look at flash memory, many bits, actually most of the bits in flash memory don't work off the bat. What makes them work is really the controller that does a lot of signal processing, for example, to make sure that those bits are read correctly. We need to do that a lot more in DRAM also, and I'm going to show you some evidence from the field. So that's the technology end. On the higher end, we have a lot more problems also. Basically, data access is a bottleneck. I'm going to give you some more numbers. Energy and power are bottlenecks, and data movement energy dominates computation energy. And today, we're in a situation where we really need to improve performance, energy, and sustainability all at the same time. We're not in the regime where we can say, oh, I'm going to improve performance by 1%, and I can tolerate 3% power cost. Those days are gone, basically. we really need to improve all of the metrics. And we can do that by minimizing data movement or rethinking the system. So basically, today, we're squeezed in the middle. That's why I'm making the case. And that's why this picture, crossing in memory landscape, actually showed a similar picture 8 years ago when I gave a lecture in the area. This picture was this much at that time. Basically, people are building interesting systems like 3D stacking. You can put logic underneath memory layers. I'm going to briefly talk about that potentially later. People are experimenting with DRAM chips. But compared to 8 years ago, more recently, people have actually been modifying the DRAM chips to put processing. This is a startup in France. It's called UpMem. They basically have DRAM chips. Inside the DRAM chip, next to each bank, you have a general purpose processor. So you don't need to move the data outside the DRAM chip. And we've been experimenting a lot with their chips. We show that actually this is useful for some applications. And then it's not just startups, but also major companies have built prototype DRAM chips where they can do processing to accelerate, especially machine learning workloads. Samsung is one, SK Hynix is another. Samsung and Meta built these, let's say, boards where you can actually have many DRAM chips and then a buffer chip, which has an FPGA that you can program to accelerate recommendation systems, for example. So you can see that these processors are essentially either inside the DRAM chip or very close to the DRAM chip. And then also system companies like Alibaba have been building their own DRAM chips to accelerate, again, machine learning recommendation system type of applications. So the future is looking nice right now, as you can see. And there are many other companies that are doing experimental chips and startups. And if you go to circuits conferences, for example, you will see a lot of papers that have built real chips that can do processing in some sort of memory. So, OK, so that's good. And then there's more. Today, we have the Compute Express Link interface, which enables decoupling of compute and memory nicely so that you can actually push some computation to the memory end. And you can see some papers, this is from SK Hynix, that talks about how they accelerate a database application, for example, near memory. So this is just to say that things are happening right now. It's not just academia that's talking about this. But let me give you the broader perspective, and feel free to stop me again. So we always thought that actually memory systems should be designed from a systems perspective. You should not really design computation and memory separately, but you should think about the entire system. Memory system should be designed so that you can actually enable scaling of it using a systems perspective. I'm going to give you the low-level perspective first. So why are we having difficulties in memory? I'm going to give you one example. If you're interested in this, I have a lecture at NCSU tomorrow that talks about RowHammer specifically. So you're welcome to come over there. But basically, together with Intel, we've shown that you can induce errors in most DRAM chips predictably. You keep hammering a row, accessing a row repeatedly, and this leads to errors. So clearly, it should not happen, right? And this predictable errors lead to safety problems and security problems. I'm going to briefly mention what it is, but I'm not going to go into a lot of detail. Essentially, if you look at DRAM, and DRAM is essentially all memory market today, you have subarrays that look like this, which are a bunch of rows. And if you want to access some data from a row, you need to activate that row, meaning that you need to apply high voltage to that row. Now, if you want to access some other row, you need to deactivate this row, apply low voltage to that word line. Now, if you keep doing this repeatedly, which is a legal operation, activate, precharge, activate, precharge, activate, precharge, a CPU could be doing this, and a FPGA, a GPU could be doing this. It turns out in modern DRAM chips, some cells that are vulnerable in physically adjacent rows get corrupt. So you lose data. This clearly should not be happening. Nothing should be changing in DRAM if I'm doing activate, precharge, right? Let alone other rows, which may be belonging to some other application or the operating system. So clearly, this is a reliability problem. And the reason this is happening is because cells are too close to each other. We built memories that are quite dense, and cells are too close to each other. Access to one cell really affects what happens in other cells. So we call this the hammered row. We call these the victim rows. And we showed essentially in 2014 that more than 80% of the DRAM chips that we tested were vulnerable. Today, 100% is the number at the device level. All of the chips that we can actually test at the device level is vulnerable to this effect. And this is one of the technology scaling problems that I'm talking about. And the solution to this, I believe, requires computation inside the memory. I'm going to talk about that briefly. But I think the problem we have if you have this sort of failures is this is not just a reliability issue, but it's also a security problem and also a safety problem. So imagine a self-driving car, which is vulnerable to this effect, right? So you need to actually solve this. And I like this sort of paper that people write. Forget software, hackers are exploiting physics. It's good to think. I like the message over here. I mean, I don't like the forget part, of course, but it's really, we need to really think about the entire stack. OK, so that's RowHammer. We wrote a lot of papers on it. Again, you can come tomorrow. Why am I telling you this? Within the context of this, the solution requires intelligent controllers, just like we do in SSDs. And I'm going to give you the industry solution. If you want to get the full story, come tomorrow. Finally, industry is writing papers about it. This is ISSCC this year, a major circuits conference. SK Hynix wrote this paper where they talked about RowHammer publicly. And they basically said they have multiple solutions inside the DRAM chips. And essentially, the solutions are similar to what have been proposed. Essentially, there's computation inside the DRAM chip to solve this problem. They have counters associated with each row. And if a row is activated by more than a threshold, they do some preventive action internally. They don't talk about it a lot, but we can guess what those are. And they claim that they reduce the vulnerability. Now, they do not make the mistake of claiming that this is perfectly reliable, which is good. So that's an improvement in industry. But basically, this is some intelligent control inside memory. Of course, after seeing SK Hynix's paper, Samsung had to put their own paper on archive, which is very hard to read. But you can see that they also have some sort of solution in their chip also. OK, so I think it's good to think about these things. These things are going to get worse. As we try to push for having more density in our memory chips, because we need to do that. We are generating a lot of data. We're going to see more and more of these noise effects that are appearing. And this is a paper that we presented at ISCA that basically shows that there are other redisturbance effects in DRAM. Again, if you want to know about it, come tomorrow or watch this lecture that I gave at Stanford recently. So you can say that, OK, these are old memories, right? DRAM, maybe SSDs. What about newer memories like phase change memory, RRAM, et cetera? Unfortunately, all of these memories require some sort of intelligent controller. They have endurance problems. They have some other reliability problems. I believe as memory scales down to small technology nodes, high densities, you really need some way of intelligently managing it. And that requires computation next to memory. OK, so that's the message over here. Any questions? Otherwise, I'm going to switch to the high level, give some motivation, and then I'm going to ask you a question. Should I keep going? OK, I'll keep going. So high level. High level, I think things are even worse, perhaps. Low level, you can say, oh, technology scaling is not going well. People are trying hard, putting intelligent controllers. High level, I think we're having problems that I don't think we quite quantify well. Because at the high level, if you think about it, like if you ask some companies, they will say, oh, GPUs are the way to go. Yes, but at what cost? I think I'm going to talk about at what cost over here. Basically, I think today we're having a lot of data access issues. Energy consumption is a problem. If you want to build a huge GPU cluster, you're actually, in my opinion, wasting a lot of energy. And data movement energy actually dominates computation energy. In my opinion, we need to think about like a bigger picture as opposed to, OK, accelerating the next machine learning model. Do we want a world that looks like this? Or do we want a world that we cannot breathe in? And I think computing power is actually going to affect this a lot going into the future. I think as humans, we're greedy. We want high performance, energy efficiency, sustainability all at the same time. And if you actually want that, or even a fraction of it, we're basically not doing things right when we design our systems. Basically, our current design principles from the very basics of how we design computers is causing great energy waste because we're moving data between the data storage and processor. This is causing energy waste. OK, we try to overcome the performance loss of this by adding a lot more complexity to our systems. For example, we add many cache hierarchies that I showed you. We add prefetching mechanisms. We add multi-threading mechanisms. We have heavy out-of-order execution engines. All of these add complexity to our system. And they compound the energy waste, especially when they don't work well. And there are many workloads where these hierarchies or these mechanisms that we add to the system, both hardware and software, don't work well. So we're in this vicious cycle where we are trying to performance loss caused by data access. And that's causing a lot more energy waste also. So there's energy waste because of data access. And then there's energy waste because of the mechanisms that we add to our system to overcome the performance loss of the data access. So I think we really need to rethink the fundamentals. Again, I'm not talking about something new here. People have actually thought about it in the 1960s, maybe even earlier. Basically, processing of data is performed far away from data. We're very processor-centric. All data is processed in the processor. And when I think of the processor, it's not just a general-purpose processor. It could be an FPGA, GPU, accelerator, whatever logic, essentially. And this happens at great system cost. And we know about this. Clearly, people have written articles. This is one of my favorites. Dick Seitz, who was the chief architect of alpha processors, after they designed a flagship alpha processor, he wrote this one-pager that basically says it's the memory stupid. Basically, he said that we designed this alpha processor, which is quite capable. It's able to finish 4 instructions every clock cycle. But on this important workload that we think we designed it for, it's finishing 1 instruction every 4.7 clock cycles. That was a database workload. Basically, it's operating at 5% of its efficiency. Why? Because it's waiting for data. And he basically ends this article, 1996. I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. So this is my own PhD thesis, where we essentially show the same thing. Together with Intel, we analyzed all of their workloads that they used to design their processors with at the time. And we found out that most of the time, the processor is waiting for data. If you don't believe the excited, you don't believe me. Since everybody released Google, Google also released their analysis in 2015. It's a beautiful paper, actually, where they show that most of the time on all of their data center workloads, according to them, the state-of-the-art processor is waiting for data. It's really retiring or finishing instructions 10 to 20% of the time. So clearly, this should point that we're not doing some things right. OK, that was performance. Energy is even worse, as I mentioned. This is actually data from Bill Daly. You can argue with all of these numbers. These are old numbers, but the trends are the same. A complicated arithmetic operation is much cheaper in terms of energy compared to a memory read or write. And the differential is really 2 to 3 orders of magnitude. Memory access is much more expensive. So this should already raise the question. When I'm doing an arithmetic operation, does it really make sense to bring, let's say, 2 pieces of data, pay that cost twice, and then do the simple arithmetic operation and return the data back, pay that cost once more to memory? Now, if you actually do the calculations, how much locality, how much reuse do you need to get out of this data so that you can overcome this energy differential? That reuse tends to be thousands of times. OK. And if you actually look at simpler operations, which is what people are trying to do, especially in machine learning these days, this is not that simple. It's a 32-bit operation. The differential is much worse. Basically, a memory access is 6400x less energy efficient compared to a simple arithmetic operation. And if you include storage now, that number actually multiplies by about 10. So it's really, if you think about it, it's kind of crazy that we're really spending all this energy to do this computation that's really cheap. And the computation is cheap because we've been quite successful in our designs, right? Technology scaling, Moore's law has enabled us to make that logic operation extremely good. So we're kind of making things worse by scaling the logic. The problem is memory and interconnect are not scaling as well. OK, so that's why we see these numbers. At the system level, more than 60% of the system energy spent on data movement. And actually, that number is even worse in applications that we really care about, more than 90%. And these papers are a lot more data. I'd be happy to talk more. So basically, I will argue that we do not want to move data. We really need to have a paradigm shift and enable that paradigm shift in a model where we can have minimal data movement. We need to enable computation where it makes sense, where data resides, essentially everywhere, in addition to the processor. We don't have any option today, any other option in the processor, and make computing architectures more data-centric. Clearly, this is easier said than done. I'm going to demonstrate it with memory, but I believe we need to do this anywhere where data resides. So we need to do this in the sensors. We need to do this in the tape, potentially. We need to do this in the network. We need to do it in the caches over here. But I'm going to talk especially about main memory today. If we have time, maybe I'll talk about storage also, because that's also very interesting. Essentially, we have applications stored in memory. And the processor, we're going to use an accelerator model in a more futuristic incarnation of this sort of idea. Everything is a distributed agent, basically. There's no processor, in a sense. There's no master. Everything is really doing operations, and then you're coordinating. So it's a distributed system. But now we're going to suppose that processor is offloading some computation to memory, asking the question, memory, can you do this operation for me? And the memory returns the results. So the data doesn't move, but the function moves from the processor to the memory device. There are many questions, even with this accelerator design, basically. How do you design the memory and the controllers? How do you design the processor and communication units to enable this? How do you design the software and hardware interfaces? How do you design the system software compilers and languages? And how do you design the algorithms to take advantage of the processing capability inside the memory itself? And I would argue that we need to also rethink the theory of computing, because if you think about the theory of computing, it's very processor-centric, right? What we do is we really count operations. But maybe that's not what's important. Maybe what's important really is how we move the data, right? So we don't have that data-centric theory of computing today. So that's why it's an across-the-stack problem. That's why it's exciting. That's why it's daunting. And that's why it's not easy to move the industry overnight, right? OK, so I'm going to talk a little bit about techniques right now. But clearly, we don't have a lot of time to cover everything. We've been writing this archive article that's online. You can find it. We're going to update it soon with more recent techniques. If you have any feedback, I'd be happy to incorporate. And we also have a processing in memory course that people can attend. We also have been holding a lot of tutorials. Okay, this is the place where I'm going to ask you a question after giving some, since nobody asked questions. But maybe I should ask you the question. Are there questions right now? Okay, so I will argue that we need to think differently from past approaches. Now, I'm going to define some terminology. I'm not going to define a lot of terminology, but there are two ways of doing processing in memory. This used to be called logic in memory in the past, but these two are fundamentally different. So you have processor and you have memory. Processing near memory says, get the processor or logic closer, 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 such that at some point it's coupled with memory. But still, memory is memory. It stores data. Logic is logic. It operates on data. So there's some distinction between these two. I call this processing near memory. This is easier to do. That's why industry is adopting this part more easily right now. And I believe you'll see more and more processing near memory in the short term. Processing using memory is fundamentally different. Logic, maybe I'll call it processor or logic, and then memory. Forget about the logic. We have this memory. It could be any type of memory, SRAM, RRAM, DRAM, flash memory. I'm going to think about this memory as not just a storage device, but a computational device. Basically, I'm going to look at the analog operational properties of the device and use it to do computation. And this opens up a whole new world of possibilities. And this has not been done as much in the past. When people proposed logic in memory in the 1960s papers, they were all processing near memory. But now we have an interesting opportunity. We can exploit the analog operational properties of the memory device itself to do computation. And this is much more efficient fundamentally. In the end, this is much harder to adopt also. That's why it's a research topic that is not adopted yet by industry. In the end, I believe we need to combine both because there are some capabilities that you cannot have processing using memory, at least as far as we can understand right now. So in the end, it should be a combination. Now, my question to you is, which one do you want to cover? Processing using memory, long-term, exciting? Okay. Processing, okay, there's more votes right now. Processing near memory, short-term. I'm not going to call, okay, some people want processing near memory, but I think you lost. I saw more hands for processing using memory, which is usually what happens, but I kind of set the stage also to get the answer. But I'm not going to cover processing near memory, but there's a lot going on here right now. This is actually fascinating. I'd be happy to talk to people about it. Let's jump into processing using memory. I have more taxonomy, but I'm not going to talk about that. If you're interested, you can look at the slides. We're still going to use memory as an accelerator. And I'm going to show you some research that we've been using, doing in DRAM. So DRAM is a technology that's very difficult. It's very changed the technology, but you can do a lot with DRAM actually, which is fascinating to me. So we're going to do processing using DRAM in main memory. And I'm going to talk about some works. Clearly, there's a lot of other works in SRAM, RRAM, flash memory. If we have time, I'll talk a little bit about flash memory as well. So basically, the gist of it is we can do a lot in DRAM. We can do bulk bitwise and or not and majority operations. We can do copy initialization operations. We can do true random number generation. We can do physical unclonable functions. And we can do more complex computation using lookup tables using the analog properties of DRAM. I will not talk about all of these. Most of these you can do at low cost. And I'm going to show you a basic idea, but not all of these are based on that idea. And you can get significant performance energy improvements in these operations. So let's dive into it. I'm going to start by cheating, meaning not even computation. Data copy and initialization. It's actually a fascinating aspect. So we do a lot of data copy and initialization in our workloads. For example, when the operating system deallocates a page, you need to initialize it, right? Imagine initializing a 10 terabyte database. It takes a long time today, basically. Today, how do we do it? We bring the data into the processor, and processor zeros them and writes them back. So there's no locality in this process also. I mean, there are optimizations you can do, but in the end, you need to write the data back so that you get zeros. Now, I will also mention that in that beautiful paper that I mentioned from Google, these folks showed that 5% of the execution time in their entire data center workloads is spent on these two function calls, memmove and memcopy. This is fascinating to me. Two function calls accounting for 5% of the execution time. OK, so how do we do in future systems? So if you show today's picture to, again, a 10-year-old child and say, oh, I want to move this page, 4 kilobytes, to this page, 4 kilobytes, inside memory, what should I do? Hopefully, they will not come up with going through the processor. My feeling is that it's easier for them to come up with this. I'm going to test this, by the way. Basically, why not just move the data inside the memory, right? Why do we have to go through the processor for this operation? Okay, clearly this will buy latency for us. This will fix some of the bandwidth issues that we're having on the perhaps the biggest bottleneck that we have in the system, memory bus. No cache pollution. You could eliminate that today with some effort. No unwanted data move. Basically, I'm going to show you a mechanism that takes us 1,000 nanoseconds, which is a 4 kilobyte page copy today, to 90 nanoseconds unoptimized, and 3.6 microjoules spent on that copy to 0.04 microjoules. The idea is very simple. We're going to exploit analog operational properties of DRAM. If you look at DRAM, this is the subarray that I kind of showed you earlier. We want to copy one row to another row. So we first activate the source row, which brings the data into the sense amplifiers in DRAM. This already exists, all of this, so that you can read the data. And then we're going to do something slightly different. We activate the destination row while deactivating the source row, which will connect the sense amplifiers to the destination row. Essentially, we use the sense amplifiers as a buffer to move the data from the source row to the destination row. Clearly, we're moving some data, but we're not moving the data all the way back through a narrow channel and wasting a lot of energy. And these interconnects are already there. OK, so that's the idea, basically. 2 consecutive activates, negligible hardware cost if you want to do it completely reliably. And basically, you get significant improvements in terms of performance and energy. And if you can read the paper for application level impact. So what's fascinating is you can actually do this in real DRAM chips today. These folks built up on our work. They took the soft-MC infrastructure that we released for other purposes, and they violated the timing parameters in DRAM such that they could get these back-to-back activates that we discussed. And they showed that you could do this row clone operation in DRAM chips today. So it's beautiful. And DRAM chips are not designed. This is not a legal operation in DRAM, but DRAM is capable of this. So imagine what else DRAM is capable of if you can do this. So we built on their work and released this FPGA-based infrastructure, which we open source. So if you want to play with this sort of thing, this is a good playground, in my opinion. You can take this FPGA-based infrastructure. What we do is we can actually run end-to-end applications on this RISC-V processor. And when you get a copy operation, that RISC-V processor ships the operation to the memory controller, which is FPGA. And the memory controller violates the timing parameters, so it can actually do the copying inside memory. We also do true random number generation. So if you get a rand call, it gets offloaded to the memory controller. So you can actually test things end to end. If you're interested, you can take a look. And we see significant benefits because the RISC-V processor is pretty wimpy in this particular case. So you can actually do real testing with this sort of thing with real DRAM. So I think that's fascinating. And the reason it's fascinating is it shows that real DRAM chips are actually capable of this, even though they're not designed for it. You can get this operation very reliably. OK, so what else can you do in DRAM? I suggested that I'm going to talk about computation. So you can actually do some computation. I will say that new memory technologies are actually even more capable. If you can get them to the scale of DRAM and the cost of DRAM at some point, these will be very interesting. Right now, they're in more or less experimental stages, in my opinion. But it's good to work on them. So I'm going to introduce this idea of triple row activation, which actually applies to other technologies also, not just DRAM. We applied it to flash chips, and we've shown benefits in real flash chips. I'm going to talk about DRAM. In DRAM, I'm showing you here 3 rows, 1 cell in each row. But imagine one row maybe 4 kilobytes or 8 kilobytes. So you can do this operation concurrently on many bytes. And then this is the sense amplifier over here. So if you concurrently activate these 3 rows, based on circuit level principles, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get this discharge state at the end, because of the charge sharing principles, basically. Of course, there's variation, et cetera. We're going to talk about that separately, potentially, if you have questions. Yes?
How do you activate multiple rows? You're using separate decoders? What's the mechanism?
That's a great question. Basically, this goes into a little bit more detail, but in our, at least how to do this reliably, we have a separate area in DRAM that has a separate decoder. And you move the data from the data rows to that separate area and you can only do the triple row activation in that separate area. And that's very low cost, because if you actually are able to, if you want to provide the capability of activating arbitrary rows in DRAM, that's a very difficult task to do. And it also has reliability issues. Yeah.
Thanks.
Sure, that's a great question. And then there are also other issues that I'm not going to cover. But the basic idea is this. So this is a bitwise majority function, which is computation. If you read Knuth, volume 4, I think he talks about the beauty of bitwise majority function. Bitwise majority is great. You can re-express it using simple Boolean algebra. If C is set to 1, you get the OR of A and B. If C is set to 0, you get the AND of A and B. Now that's great, right? But that's not functionally complete, meaning that you cannot do every operation because you're missing an inversion operation, which is actually not that bad because it already exists in DRAM, right? If you actually activate one row, you get the value here, and you get the inverted value over here. So in this paper, we proposed a hard-to-implement mechanism that actually takes this value and puts it back. But later works improve that mechanism, so you can actually have that inverted value also in the array. So essentially, you can have a functionally complete DRAM by having majority or not operations. Now, what can you do with it? This requires, of course, changes to DRAM. But I'm going to talk about some more recent experiments that we've done that show that you can actually do this in real DRAM chips with some success. OK, so if you actually have this reliable in real DRAM chips, you need to think about your algorithm differently. Basically, you're operating on many bits concurrently. We call it bulk bitwise operations. Imagine that one row is 8 kilobytes, and you have thousands of subarrays. You can actually do this operation on 8 million bits at a time. If your application requires a lot of bit vectors, which is present in a lot of databases, actually, and some web search engines, people have built these databases and web search engines to maximize the bitwise operation so that they can actually use the GPUs to parallelize things. These are good fits for this sort of processing. And then we cover other things also in the paper. Actually, some graph analytics is quite, especially if you're re-expressing your graph operations in terms of set operations, you can do a lot of bitwise operations on graph. We had a paper at Micro 2021 that talks about it. I'd be happy to talk about it. But basically, we showed significant performance improvements. This is the bit-weaving database that was developed by Jignesh Patel's group at the University of Wisconsin. And we took their database, and we put it on our simulator. And essentially, we show significant performance improvements, as well as energy improvements, if you exploit this sort of substrate. OK, if you want to learn more, you can read the paper. Clearly, there are other papers. More recently, we targeted programming. Feel free to ask questions, by the way. How do you actually make this more easily accessible to the user? Because the user can express operations, but how do you interface with it? So in this work, a few years ago, we showed a way of generalizing this mechanism. Basically, user can provide any operation, desired operation, using a circuit drawing, let's say, and or not logic. It could be a convolution, it could be a matrix multiplication, it could be division, anything you want, basically. Anything you can express like this, which is essentially all things, if you're thinking with the right mindset. And then we take that using CAD tools that were developed for quantum computing. We actually convert it into a majority and not logic, and then optimize it. And then express it using a microprogram that is actually doing these triple row activations and row clone operations inside the DRAM, plus some allocation of rows, et cetera, that I'm not going into. And basically, you can associate an instruction with it. And when this instruction is used by the program, it gets shipped to the memory controller. And the memory controller goes to this microprogram to execute that instruction. So this is a way of actually integrating this sort of bulk bitwise operations to the existing programming model. There are some issues that I'm hand-waving over here, but they're covered in the paper, and I'm happy to talk about those. Now, if you do this, you can actually execute even more applications more easily. And we show that you get significant performance and energy efficiency improvements compared to CPU and GPU with this sort of mechanism. This sounds fascinating to me. OK, so SimDRAM, one of the downsides of this is the granularity. So you need to operate on 8 kilobytes of data if that's your row size. So we tackled that in our more recent work, which I'm not going to talk about. This is going to appear 2 weeks later at HPCA. We're going to present it. But basically, this tries to make it more programmable and also reduce the granularity so that you can actually handle more applications this way. And you can actually fit different types of operations in different parts of the subarray. So in general, with these mechanisms, data layout tends to be a problem. You need to lay out your data so that you can operate nicely in processing in memory. And that's usually the hairy part. And the other hairy part is the virtual memory, which we will talk about maybe. OK, so more complex operations are not easy to do. So I'm talking about bitwise operations, right? Usually, the way you do multiplication or you do addition is you do bit serial addition, right, with these sort of mechanisms. And that's what we do. If your data size grows, if you want to do multiplication, if you want to do division, what I just described becomes less efficient. So basically, the latency increases. You can overcome the latency by doing massively parallel operations. If your application has that, that's great. But we also develop lookup table-based execution mechanisms so that you can actually do better multiplication, division, et cetera. This requires some changes to DRAM, but I'm not going to talk about that right now. So what else can you do in DRAM? I'm going to skip this one because this is the other side of the coin. So you can actually, we've shown that you can actually generate true random numbers at high efficiency and high throughput in real DRAM chips. What we do in this work is we tested a lot of real DRAM chips, LPDDR4 chips. If you violate the timing parameters, meaning that you don't give enough time for the circuits to sense or settle, some cells fail randomly. And these are great true random number generations. We call true random because we believe that the process is a physical process. It's a sense amplifier noise, essentially. And we show that you can actually get true random numbers at high throughput. This is fascinating because if you want to push computation to the memory side, you want to push some security critical functions. In fact, I believe that security can benefit a lot by pushing computation next to the data, because one of the issues with security today is you're moving data all around and somebody can leak that data while the data is being moved. If you actually localize the computation on the data with some security functions, you do need a true random number generation mechanism also inside the DRAM. Yes?
It may not be specific to this slide, but
Sure.
do you worry about precision of the computation? Like how many a lot of applications with high data rate also require a lot of bits per number. And so I'm just wondering, that's a major factor.
Yes.
And not in some of these, but
Sure.
Does this apply to that problem?
Yes. So if you're we do look at it. Yes, precision is important. That's the difficulty is in some of these cases, very high precision is very difficult because of the bit serial nature of this. Yeah, people are working on it. People have proposed like building on some of these works, adding like floating point capability inside the DRAM, but that requires a little bit more area. I'm not suggesting this is a good fit for every type of operation. That's why I suggested you can do this processing using memory very efficiently for some operations, and some operations you cannot do it with. Just put some logic near memory or inside memory. That's why I think these two paradigms need to be implemented together. But maybe someone will discover how to do precision on this one also. A lot of these require rethinking the algorithms also, because in the end, the substrate is very capable. It should be capable of anything, right? Because it's functionally complete. You just need to rethink your algorithm, which is easier in some cases and much harder in some other cases, right? Yeah. Okay, so we've been working on random number generation as well. So this is also coming up at HPCA. This is also fascinating to me. Basically, DRAM chips are actually already quite capable. In this work, we show that you can actually implement NOT, NAND, and NOR in DRAM. I'm going to leave the suspense to the HPCA presentation. And we show that you can actually do many input NOT, NAND, and NOR in real DRAM chips. The basic idea is very similar: violate the timing parameters. If you carefully violate the timing parameters, in DRAM chips, you can activate 16 rows. In some cases, we've seen 1,000 rows activated together. Now, again, based on chart sharing principles, it's a 16 input majority function, right? So by manipulating some of the inputs, you can get NAND, NOR, etc. So this is fascinating. Of course, it's not perfect, meaning clearly DRAM chips are not designed for this purpose. We're violating the timing parameters, right? But we get quite high success rates, meaning like 98% of the bit operations actually are correct. Yes?
Maybe you'll get to this later, but
Sure.
let's say you were going over to the DRAM manufacturer. You
Yeah.
said, I've got this great idea. I
Yeah.
need your help. What would you ask them to do differently?
First of all, in general, they're not open to these ideas. For example, let's pretend they are. So basically, I would start with row clone, right? Row clone is a very simple operation. I would say basically, so I think a lot of these things are chicken and the egg problems, right? If you don't have this in hardware, software people will not build the infrastructure to use it. I would start with very simple operations like, okay, copy support, in DRAM copy support. Very simple one, like fix the granularity to a row granularity, put it out, let people develop software, and hopefully get benefits. And over time, I think that cycle will hopefully be broken. That would be my recommendation to them. But you're asking what I would ask from them, I think.
Well, I mean, you're making things happen by breaking the rules.
Exactly. But I would like them to do it like without breaking the rules. Basically, actually, in our earlier papers on row clone, we said, okay, add some commands.
So
Don't break rules.
The other aspect would be, there might be things you can't do now, even when you try to break the rules.
Exactly, yes.
Is there something else like, man, I'm so close to being able to do this, but I can't quite break the timing in the way I need?
Yeah, absolutely. So, for example, moving the data, we cannot do it regardless of however we break the timing across subarrays.
Okay.
Even though most of the infrastructure we know exists internally. You have these different DRAM banks, and they're connected with a bus. You can read data from one, write data into another. We just want to read data from one and write data into another without going out of the chip, right? So that's what I would ask, basically. So there's a lot of things like this. I mean, I'm happy to talk more. But making some of these reliable is something I would ask, although some of these are very hard to get completely reliable, in my opinion. There are a lot of variation effects, etc. That's why I believe that this is a paradigm that's harder to adopt than processing near memory, right? We know how to make logic reliable, even when it's in the DRAM process. But we don't know how to make analog operations completely reliable yet. OK. And there's also this work at Archive, if you're interested. So this also shows that DRAM chips are quite capable. OK. How much time do we have? 5 minutes, 10 minutes? OK. Approximate 10. OK. So maybe I'll mention that you can actually do everything I suggested in Flash as well. So we verified this in real Flash chips. I will not go into detail over here. And in real Flash chips, you can also do multiple row activation. Essentially, you can do a 32 input AND operation, bulk bitwise AND in real Flash chips. And we tested with real Flash chips. You can do OR, you can do XOR, etc. I'm not going to cover this because we don't have time. But you can read the paper if you're interested. And this also leads to significant improvement. So you can do in-storage processing as well. And clearly, you can do this NVM, but I'm not going to talk about it. There are experts here who are working on NVM, RRAM, etc. So since you voted for processing using memory, I'm going to skip processing near memory. There's a lot over here, clearly. Or do you want me to talk about it like quickly? Quickly, OK, you want it. OK. No, I'm not extending the talk, so there's a request. So there's a lot here. But I'm going to give you some things. So here, I think processing near memory, we need to think about accelerating things. And when we first started doing things, we wanted to accelerate important applications. Clearly, machine learning is important, and there's a lot going on in near memory acceleration. But we also wanted to look at graph analytics at the time. There are two ways of looking at this, I think. One is, if I have processing capability near memory, how do I accelerate an important application? How do I build a system? And the other way is, if I have processing capability near the memory, how do I change things as little as possible to take advantage of it? We explored both directions. I'm going to talk about how do you change the entire system direction, which is, again, not going to happen overnight. But it's interesting. So we looked at graph analytics. Graph analytics is clearly interesting. Whenever I give this talk at Meta, they basically said, oh, we have much more than 1.44 billion. That's why I said circa 2015 over there. Anyway, basically, if you look at graph processing, there's a lot of frequent random memory accesses and little amount of computation to cover for it. So locality is scarce there, not completely. It depends on the graph and layout, etc. So that's why we thought actually processing near memory is a good idea over here, because CPUs clearly cannot exploit locality in these applications at a large scale. So what we looked at the time was essentially memory stacked with logic. And today you have these devices, actually. HBM is very close to this. And there are other true three-dimensional technologies that are under development, like monolithic 3D technologies. But basically, you can have a logic layer that's quite capable underneath memory layers. And memory layers can be connected at high bandwidth and low latency to that logic layer. That's the idea. So what did we propose? The idea is to have a distributed system of these things. Essentially, we're going to think about graph processing acceleration. We're going to offload computation to this distributed, I'll call these cubes, 3D cubes. And in each cube, in the logic layer, you have an array of processing cores. Each processing core owns the memory on top of it. And if you want to do an update to a graph node, you partition your graph across these nodes and across the distributed system of cubes. And if you want to do an update on a graph node, you send a message to the core that hosts that node. Essentially, this is you ship the function to the node that hosts the data, as opposed to moving the data all around. And that's the idea. You program it using distributed system programming mechanisms. You do some graph partitioning, which you have to do anyway in general, so that you exploit as much locality as possible that you can discover. So with better graph partitioning algorithms, this actually gets better. And you program it using remote procedure calls. What's inside each of these cores? It's a very simple in-order core. We also looked at accelerators, but I'm not going to talk about that. And this in-order core does the processing. It doesn't need to be hefty, because the data is not a big bottleneck, basically, hopefully. I've already said this. So the programming model is very similar to distributed system programming, except we do it at a micro scale, as you can see. And we have prefetching mechanism because there's ample bandwidth available to each of these cores. So these are the systems that we compared with. These are essentially processor-centric systems with different types of memories. They're all limited by, essentially, they have the processor-memory dichotomy, and they're all limited by the memory bandwidth, right? Because you have limited number of pins, both inside the memory as well as inside the cores. So Tesseract doesn't look like this. Essentially, processing and memory are coupled in this cube, and you have a distributed system of cubes. That's the idea. So at the time, we had 8 terabytes per second bandwidth available to all of the cores, in this case, 512 simple cores. So if you do the comparisons, we looked at 5 graph processing algorithms, and we saw that you get significant performance improvements averaged across all of those graph processing algorithms. So I think this is fascinating. Of course, it requires a rethinking of the entire system. Later works improved on this. They looked at a lot of different parts of it, and they optimized it. I think that number has increased to about 100x or so, which I find fascinating. Energy reduction we showed was about 8x. I think later works also improved this. So that's the idea over here. I think this sort of thinking is good. I believe actually machine learning is very capable of being accelerated like this as well. Of course, you need to design the accelerators nicely, right? An in-order core will not work for machine learning. You really need a machine learning accelerator inside that cube that I talked about. Okay, I'm gonna, I think, skip some of these because we don't have a lot of time. If you're interested, you can take a look at the slides. But I'm going to talk about adoption issues, which are really important. The other issues I think we can cover, but adoption is really interesting, I think. Okay, not here. Sorry. So both of these paradigms have adoption challenges. I think using memory has a lot more adoption challenges than near memory. But both of them actually have adoption challenges. So what are those? I think this is the thing that we really need to do more research on. In the end, I think it boils down to applications of software, right? We have to show benefits at the higher levels. We can come up with any kind of hardware, but if that hardware doesn't show benefits at the higher levels of the stack, then that's not interesting. And that's not enough, because you can show huge benefits in applications of software, but these issues may prevent adoption, right? How do you program this? Right? Some of you may know the IBM Cell engine, right? It was a great potentially processor for its time, but it was very tough to program. How do you provide system and security support? Coherence, for example, is important, I think, especially if you want to partition applications at a finer grain than offloading everything to the memory. Virtual memory is a huge, hairy issue, I think, that we need to rethink across entire systems that we have today. It becomes more difficult here. Runtime and compilation systems, I'm going to skip. I don't have time to talk about it, but our paper covers a lot of these things. And I believe we need to build infrastructures to assess benefits and feasibility. But in the end, I think what limits us is our mindset. So going back to Dan's question earlier, the mindset of computing has been extremely processor-centric from the very first level of education, right? When we actually take our first computing class, it's processor-centric. You don't think about anything else. And that's ingrained so much in essentially everything, not just industry, but in education also. So if we start changing that mindset, maybe we have a chance to change the computing paradigm. But if the mindset stays the same, I'm not sure. Then everything is a hurdle. And if I actually think about the processor-centric mindset, if I am a believer in processor-centric mindset, I would never do data-centric, right? Things are going well. I don't care how much energy we're wasting. It's scaling, right? Okay, but it's good to question that perhaps. So I think in the end, we need to revisit the entire stack. I'm going to skip these slides also. Oh, okay. Landscape today. Sorry. Yeah, we don't have time for these. But I knew that we don't have time. So if you're interested, you can look at the slides. No, not 400. Okay, so let me conclude. So I think if we want to have fundamentally efficient architectures, we need to be data-centric. If you want to have fundamentally high-performance architectures, we need to be data-centric. And I could replace that with fundamentally secure, etc. I believe we need to be more data-centric, but I'm not going to make that claim because I don't think we can prove that yet. So I think a lot boils down to minimizing data moments. So to conclude, okay, let me go back to the fundamentals, maybe. Teaching. I teach the digital design and computer architecture class. And one of the principles I teach in digital design and computer architecture is balanced design, right? There needs to be a system balance. And immediately I'm ashamed, and I tell the students this, basically we're breaking that system balance in today's systems. There's a huge imbalance, processing and memory. You have a huge data moment problem because of that imbalance. So if you want to design balanced systems, basically do what we preach, we need to be much more data-centric. And I believe data-driven data aware, but I didn't talk about that. We need to enable computation capability inside and close to memory, as well as all data storage and movement structures. I believe this can lead to orders of magnitude improvements. I've shown you some examples of that. This can enable new applications and computing platforms, especially in the genomics domain, but maybe there are other domains. I think machine learning, for example, has been enabled because of the success of GPU architectures, right? Which is somewhat less conventional compared to a CPU. This can enable better understanding of nature. I don't have time to talk about that, but that's interesting. And who knows what else? So I think the future is really bright, but we do need to do the hard work, research, design, and education across the computing stack. I will leave you with this picture. Basically, this device, is probably a computing device, but it's not resembling how we design systems, right? Computation, communication, and storage is somehow tightly integrated in this. And there's a lot of analog computation going on in ways which we simplify today. I don't believe we completely understand, and I don't claim to completely understand this clearly, right? But OK, maybe I will leave you with this slide where I acknowledge my group, because I presented their work. And if you're interested, you can read more of what they do. OK, and you can find actually all the papers online, and we open source a lot of things. If you want to get into processing and memory research, we'd be happy to help. OK, I'll stop here.
Do you have any questions for Onur?
I have some questions. So it looks like, we're talking about the processing using memory, which show a good example that how computation is done in one bank, right? So if the case is that we have a huge amount of data, we must need multiple banks to store that data.
Yeah.
And the source data and is not aligned. Maybe it's the shape is not what we want. How do we solve this problem?
Yeah, absolutely. So that's basically why we need these units to communicate from one bank to another. That's why I mentioned to Dan also, this is what I would like from DRAM manufacturers to implement. But there have been a lot of proposals to figure out how to move the data from one bank to another. RowClone has some of them, but later works also improved it. Certainly having support for moving data from one bank to another, and also moving to different parts of the row from one bank to another is important.
I mean, if we want to move the data from one bank to another bank, we also need an on-chip high communication bus or NOC or something.
Yeah.
Right? So in conventional DRAM, we only need to move the data from one bank to all of the chip because it's computer-centric. But in this case, we need to change the DRAM organization.
Yeah, absolutely.
Move data inside the chip.
Not necessarily DRAM organization. I mean, we have some works showing that basically, currently there's a bus that connects the banks, but it cannot be used to move data from one bank to another bank. Yeah. But it can be. There's nothing that limits that really. It's just not possible today in today's DRAM chips. But more advanced versions of this work clearly add like more better interconnects inside DRAM. And I think we do need that. So if you look at the picture that I showed you, the brain, the connectivity over there is huge compared to what we have inside our DRAM chip today, right?
So that may be another challenge about the memory-centric computing, right? So we reduce the off-chip bandwidth requirement, but we still have an on-chip high bandwidth requirement to move the data in memory.
That's true, but I will argue that that's much easier to solve. Off-chip is much harder and much more energy inefficient, whereas on-chip is easier to solve. And maybe we need to invest more into that. One of the reasons why, again, this mindset gets in the way. One of the reasons why the interconnect in DRAM is so simple today is because it's memory. It's not thought of as computing. If you actually think about this chip as a computing device, we would reorganize it in a different way, right? And 3D stacking technology also helps. So if you have 3D stacking logic layer underneath memory layers, you can actually do a lot of the data movements and the networking in the logic layer.
Right. Because we're going to lose this room soon.
Okay.
Let's thank our speaker again.
Hey, thank you. Oh, okay. I started it, but I guess I did the right thing.
By the way, so you are interested in today's also SRC Semiconductor Research Corporation with it. They'll be working some 100